So, hello everyone. Welcome to the live section of this course, which is Quantum Transport. So, I'm Gitanjali. I'm a PhD scholar from IIT Delhi, and I'm the PMRFDA for this course. So, in the last week, we have seen what are the transport properties for a single quantum dot. So, we have seen the charge stability diagram where we have seen the Coulomb diamond region, as well as we have seen some of the transport properties of single dot system in single electron transistor or in a single electron box or island. So there we have seen the effect of single electron charging, where we have seen the current oscillation, which we say the Coulomb blockade oscillation, because of this single electron charging effect. So for this week, we will see what are the transport properties of a double quantum dots, where we have, instead of a single quantum dot, we have a two quantum dot which are either coupled to each other through a tunnel barrier. So if you consider the single quantum dot as a artificial atom, so you can imagine the double quantum dot as a artificial molecule, because there are two quantum dots which are coupled to each other, and we can consider, or we can treat it as a single artificial molecule instead of a artificial atom. So let us see in the details about what are the transport properties of the double quantum dot. So in the lecture, so we'll basically cover what are the major concept that can be that has been discussed in the class. So we'll not go in details, and but I will try to cover all the major points from each slide, so that the concept is now also better by if you revise it. Okay. So if you look at the first figure, this is one of the SEM images of quantum dot. The dotted region here, these are the quantum dot region where the quantum dot can stay or it can tunnel to the second quantum dot depending on the uh, interdot coupling or the gate voltage applied. So this is, if you look at the right figure, so this is one of the simplest representation of double quantum dot. So VL, these are plunger gates. If you recall, these we call it as a VLVR. These are plunger gate, and VL is nothing but it controls the electrostatic potential of quantum dot one. So this is for QD1, and this one is for QD2. So VR, it controls the electrostatic potential of the quantum dot 2. So this figure we'll see in the next slide. But for now, let us see what are the transport properties in different regime. Like it can be a high voltage regime where we apply a high source to drain voltage, or it can be a low bias regime where we apply source drain voltage which are very, very negligible. So in this paper, this circuit representation of double quantum dot has been given. So if you look at this figure, the two quantum dot. So this is one minute. This is one. Let me take this one. Okay, so this is quantum dot one and this is quantum dot two. Quantum dot one has n1 number of uh, electrons or sorry dots in this system, quantum dot one, and quantum dot two, it has a n2 number of electrons, sorry, quantum dots in quantum dot two. And these two quantum dots, these are tunnel coupled through a tunnel barrier. And remember tunnel barrier, these are the symbols or symbols for circuit symbol for representing a tunnel barrier. And tunnel barrier, it is nothing but a leaky capacitor, which is in capacitor as well as resistor, which are connected in parallel. And also this two quantum dot one, it is tunnel coupled through this tunnel barrier to the source junction. And quantum dot two, this is also tunnel coupled to the drain side through this tunnel barrier, which is resistance RR and capacitance CR. And to control the electrostatic potential of this double quantum dot, we can um, couple this quantum dot one to a gate voltage through a capacitance CG1. And also we can also capacitively couple the quantum dot two to a gate voltage through this capacitor CC2. And there are also inter coupled capacitor which are controls the electrostatic potential of other dot when we apply voltage to one of the dots. Okay, so this BG1, BG2, they only just they control the electrostatic potential of quantum dot 1 and 2 without tunneling any electron to this source, to this voltage terminal Pg1 and Vg2. Okay, so for this case, let's see what are the transport properties for a low bias regime. So if you consider the low bias regime, so which has n1 number of electron in quantum dot 1 and n2 number of electron in quantum dot 2. So so when we say we are studying the transport properties, so we are typically looking at a region where the energy applied, so applied energy here, it is much less than the charging energy. So this means so we can derive two conclusions from this. First is that for this double quantum dot, we can see the single electron charging effect. So single electron charging, it can be possible for this energy range. So single electron charging means the electron will tunnel from one quantum dot to another quantum dot one by one. So two electron cannot tunnel at a time. Only at a time, only one electron is allowed to tunnel from quantum dot one to quantum dot two. Okay. So single electron charging effect is also possible. And second is that because they are coupled, this double quantum dot system is coupled to each other through this tunnel resistance, tunnel barrier, which is Rm and Cm. So this means that if you consider that one of the quantum dot, it is in the Coulomb blockade region. So energy is not sufficient to hard electron to that system. So if either one of these quantum dot is in the Coulomb blockade region, so that means the total transport, it is completely blocked. So this also means there won't be any transport is blocked if either one of this quantum dot, it is in Coulomb blockade region. So we are focusing the energy range where we can see the single electron charging effect. So for this energy range. So if you look at the, let's see the charging sequence. So there can be two types of charging sequence. So first one is that, so we have N1 and N2 number of electrons in the quantum dot 1 and quantum dot 2 respectively. Now we are adding electron from the source side to the quantum dot 1. So that means the electron in this quantum dot 1, it will increase by 1 and 2 will remain as it is. Now from quantum dot 1, this extra electron, it can tunnel to quantum dot 2. So we'll see the condition under which it can tunnel. So that means now the N1 plus 1, it becomes N1, and the electron in quantum dot 2, it will increase by a factor of 1. And this extra electron now tunnel to the drain side, so that we can see overall current in the circuit. So this is one of the charge transport case we can have for this case. Now we can also have another type of charge transport case where we see that already there is extra electron in quantum dot 1 and there is extra electron in quantum dot 2. So that means because it is a single electron charging process. So that means we can't add one electron to this. So to see the charge transport, that means this extra electron, it has to tunnel to this drain region, so that the N2 plus 1 will become N2, N1 plus 1 will remain as it is. Now this extra electron from N1, it can go to N2 because there is no extra electron in N2. So that means now the charge distribution is N1 plus N2 plus 1, and it will now tunnel to the drain side. So these are two of these processes that we can have in the low bias region. So now let us see what are the uh, charge stability diagram for this double quantum wave. So if you recall the single electron transistor, so in that case, to change the Coulomb blockade region, so we can either control the gate resistance or we can control the source to drain voltage. Sorry, we can either change the gate voltage or we can change the source to drain voltage. So there are two parameters that we can play with to control the Coulomb blockade uh, reason. So this graph you can recall, under different gate voltage we can change this IV characteristics, and by combining what is the current at different gate voltage, different source to drain voltage, so we have seen a Coulomb diamond reason. So this is for the single transistor case. Similar study we can also see for a double quantum dot system. But here, in addition to, so we have three voltages to play with for this charge transport for a double quantum dot. Now we have VG1, VG2, also we have a source to drain voltage. So let us see what are the transport charge diagram will look like. So to start with, so we can study the charge transport case by case. So we'll first, because there are a lot of resistance which is in the circuit, so we can study this whole charge transport by taking different cases. So for the first case, let us say, so we'll start from the simple and a totally unrealistic case, so that we can also understand what will happen to the next case where we have any non-zero value of the circuit value. So for the first case, we consider that the CM, which is the interdot capacitance, and CG1 and CG2, these are 0. So this means that the charging effect, that is the charging effect and what is and the discharging effect of the quantum dot 1 and quantum dot 2, they are completely independent. So because there is no capacitance which can affect the coupling between this two quantum dot. So for this case, if you add any extra electron on quantum, let's say quantum dot 1, then it won't induce any charge on quantum dot 2. So that means it don't affect quantum dot 2 if you add one electron on quantum dot 1. And similarly, if we have one electron on quantum dot 2, then the quantum dot 1, it remain unaffected. So for this case, what we have is that the charge stability diagram. So remember that we are only focusing on the low bias region. So we'll see what happens in the higher bias region. So if you recall, in higher bias region, we'll see a bias triangle. But for the low bias region, let's see what is the charge stability diagram. And if you look at this figure, so this is the schematic of a charge stability diagram for the uh, case where Cm, Cg1 and Cg2 are, these are 0. So because this charging and the discharging effect of quantum dots for this case, they are totally independent because Cm, Cg1 and Cg2, they are completely 0. So here we can see that uh, if we vary Vg1 and only the state of quantum dot 2, so only the energy of quantum dot 2, it will get changed if you change Vg1. And similarly, if you change Vg2, only the energy level of quantum dot 2 is affected, but quantum dot 1 state, it will remain unchanged. Okay, so it will remain unchanged. So that means for this case, we'll see either depending on the symmetry of quantum dot, we'll see either a square lattice or a rectangular lattice. So if you look at this figure, for this direction, we are changing Vg1. So that is why the energy level or the number of quantum dot in QD1, it is changing from 0 to 1 and 1 to 2. And for this state, we can see the Vg2, it remain unchanged. There is no change in Vg2 because they are completely independent. Similarly, if you look at the vertical direction, so for this case, the Vg1 remains constant because they are independent. Only by varying Vg2, the number of electron on quantum dot 2 is changing from 0 to 1 and from 1 to 2. Okay, now this is fine. We have a square lattice and we can see how this quantum dot is getting added to Bg1 by Bg1 or by Bg2 in quantum dot 2. But the main question is that where do we see the charge? What is the physical significance of this diagram? So this physical significance, it is only when we see this intersection region where we'll see that there is three quantum dot that coexist with each other. So the more interesting reason for this square lattice or the rectangular lattice is the intersection point where which we say the triple points, charge triple point. So these are the more interesting reason where we'll see the charge transport. Okay. Because to see the charge transport, that means the number of electron, it is changing from one quantum dot to another quantum dot. So if we say, if we start with N1 to N2, so that means if there is a charge transport, that means N1 become N1 plus 1 and N2 will remain unchanged. Then we'll see N1, then N2 plus 1, then N1, N2. So this only happens at the charge transport, the charge triple point, which is this. Because if you look at this, let me better take another color. So if you look at this threaded region, so this is the reason where the charge is remains constant. The charge on quantum dot 2 or quantum dot 1 remains constant inside this shaded region. So that means there won't be any current that will flow if we are in this, if we have a voltage VG1 and VG2 which lies in this region. But once this voltage, um, once we are getting this voltage, this cross point where we can see that for this cross point, let's say if you see the one example which has been discussed in the class. So we are started with 1, 1. Then we are adding one electron to the quantum dot 1, which will give 2, 1. Then this will give 1, 2. Then again 1, 1. So for this charge transport, for a low bias region where we apply low bias. So that means if you look at this cross point, all these uh, 1, 1, 1, 2, and 2, 1, they have the same, they occur at the same gate voltage of VG1. They occur at the same point. So that means it's possible for the electron because there is a fluctuation in the charge. There is 1, 1 on one side, 2, 1 on one side, and 1, 2 on this side. For this point, all these states are coexist, means all these states are occurring at the same value of Vg1 and Vg2. So that means if you apply this amount of Vg1 and Vg2, there will be a charge, there is a possibility of getting charge fluctuation. So that means there is a possibility of getting current through this system. So the main takeaway from this square lattice of diagram is that so to see the charge transport, we have to apply the gate voltage which lies this on this charge triple point. And for this special case where Cm and Cg1 and Cg2 are 0, for this special case, uh, if you start with 1, 1 or if you start with 2, 2, these two states have the same, they occur at the same gate voltage. That means they are degenerate. So if you apply gate voltage so that you can see this transport, then same voltage can be applied to see this transport to 1, to 2, to 1, then 1, 2, then 2, 2. So they occur at the same gate voltage. So they are degenerate. Okay, so this is all about for the case where we have a both the interdot capacitance as well as the CG1 and CG2, both all these are 0. Now for the second case, which we have seen for this slide. So for this slide, what we have is that we have the interdot capacitance, which is Cm. It is 0, but the CG1 and the CG2, these are non-zero, but they have a small value. So they have a small value. So what does this mean? So this means that if you vary the gate voltage of one of the, so if we have this one, quantum dot 1, quantum dot 2. So this, or I can say it here. Okay. So if you vary CG1, let's say we are varying CG2, CG1, then this quantum dot will also get affected because of the variation of sorry, If we vary VG1, then this quantum dot 2 will also get affected. Or if we vary the VZ2, then the electrostatic potential of the first quantum dot, it also get affected. Okay, so this means the charge degeneracy point, where we have seen the charge degeneracy point for this case will get affected, even if we vary the gate voltage of one of these quantum dot. So in summary, what we can say is that previously we have a square lattice of for the charge transport, where we see N1 N2 is going to N1 plus 1, N2, then this is N1, N2 plus 1, then back to N1, N2. Or we started with a extra electron on second, also first. This will go to N2, then N1, N2 plus 1, then back to N1 plus 1 and N2 plus 1. So for this case, where we have Cg1 and Cg2, both are non-zero, but the interdot capacitance is 0 here. For this case, what will happen? Because one gate is affecting the electrostatic potential of other gate. So that means instead of a straight vertical line, we'll see a tilted line. So this is for VG1, BZ2. So we'll see a tilted line for both VG1 as well as when we vary VG. But the concept will remain same. That means inside. So let me just write down what are the charge points. Okay, so the concept will remain same, because the charge transport will occur only at this charge triple point, where three charge can coexist at same value of Vg1 and same value of Vg2. The charge transport will occur this triple point, and inside this region where the charge is constant, there won't be any there won't be any current. So we'll see current only if the Vg1 and Vg2 satisfy these values. Okay, and it will become tilted. So this is for the case where we have Cg1 and Cg2 non-zero. In the I think okay. In the last case for the low bias condition, what we have seen that we have seen a more realistic case. So instead of assuming this is non-zero, but this one is not zero, instead of assuming that, now we have all these CG1, CG2, also CM. These are non-zero. Okay. So this means because there is a non-zero value of inter dot capacitance, so that means the 1,1 state and the 2,2 state, which were degenerate earlier, now they are no longer degenerate. So they will get shifted. So the shifting, it is quite, if you look at this charge stability diagram. So for this case, we'll see a honeycomb shaped stability diagram. And for this case, what will happen? The 1,1 state and the 2,2 states, they are no longer non-degenerate. So you can see here, the 2,2 state is we are seeing the 2,2 state at higher value of gate voltage, and the 1,1 state, it is at the lower value of the gate voltage. So that means it will get shifted depending on VL and VR. And this shifting, it is because of this non-zero value of non-zero value of this interdot capacitance, which is C. And you can also guess why 2 state is getting shifted in the upward direction, because if you see the 2 state, it is having more electron, right? So that means the energy of this state is quite higher. So that means we are applying more gate voltage to this state. So that is why we'll see the 2 state in higher value of higher gate voltage as compared to the 1 state. So if I summarize all this for the low bias case, if you look at what is happening in summary, so the charge stability diagram for the low bias case. So don't confuse between low bias and the large bias. So there is a large difference between them. For the low bias case, in the lecture we have seen 3 cases, but for the higher bias case, we have only seen one case where uh, the system is more realistic. That is, none of this capacitance is zero. But for the low bias case, we have seen one by one. That is, we have started with zero value of capacitance, then we make one of the capacitance non-zero, then we make all of this capacitance non-zero. So in the first case, where we have seen either the square lattice or the rectangular lattice. So for this case, we have seen that we is in vertical lines where when we change Vg1 and Vg2 and the charge transport is occurring at this charge triple point. So we can start either this way or we can start from 2 to this. So this is for the case where Cm, Cg1, Cg2 all are 0. So that means if you label this process as A and this process is B. So A means we have started with N1, N2, and B with we have started with N1 plus 1 and N2 plus 1. And for this case, these states, the AB process, they are degenerate. They occur at the same value, occur at the same point. Okay. And for this is for the square lattice, where we have all these capacitances non-zero. In the next case, what we have done, the Cm is 0, but Cg1 and Cg2, these are non-zero. Because of this Cg1 and Cg2 is non-zero, now what will happen, this vertical line will now get tilted. Because now Vg1 is affecting Vg2, also Vg2 is affecting Vg1. So that is why the lines will, the charge stability diagram will get tilted. The charges are same. And in the last case, what we have seen is that all these capacitance are non-zero. And because of this, in addition to the tilting, we'll see that the 1 state and the 2 state, which are degenerate in this point, in the tilted one, now they will get shifted because the interdot capacitance is non-zero. So that means 1 state and 2 state, they don't have any same value of, they don't occur at same value of Vg1 and Vg2. So for this state, we see hexagonal one, and we have seen that this 1 state is getting separated from 2 state. So for this two, AB are degenerate, but for this one, AB is non-degenerate. So AB means we are referring to the charge transport process, where we have started for A, it is from N1, N2, and for B, we are starting from N1 plus 1 and N2 plus 1. But the whole, the charge transport concept, it is same for all. That is the common characteristics between this all this graph is that So the common is that the transport, if you look at the transport where we see the non-zero current, so current is non-zero only at the charge triple point. And for the hexagonal lattice where we have seen this one, for this we have two types of triple point. One is the case where we have started with the A process, and this is for B process. So that means for A we have started with 1 1, and for B we have started with 2 2. So this is what we call in electron triple point, and this is what we call as a hole triple point. Okay. The charge transport for this triple point, or if you look at the electron transport for this triple point, also this triple point, they are in the same direction. They are not different. So, but only to differentiate between this process, we say this is electron triple point, and this is we say is a hole triple point, because we are already starting with one extra electron. So we can say the movement is more like a we can just analyze that it is behaving like a hole, but there is no real hole. This is only for our study purpose. Okay. So this is for this low bias case where we have seen square to tilted to hexagonal lattice. Now for the second case, so this part I have already covered, so there is no need of going into the details. We'll see what are these lines referring to: blue, green, and is that red lines. So these lines are significant in the higher bias region. So we'll see what this line refer to and how they affect the charge transport. But for the now, these are some of the mathematical formulation. Like we can calculate the electrons. Just go through no need to remember the whole equation, but you need to remember what is the dependence. Whether, let's say, if you see this figure, so for a honeycomb lattice, if we recall from the single electron transistor, by studying the Coulomb diamond region, we can calculate what is the period of Coulomb oscillation, and from the period we can calculate what is the gate capacitance, because these are the period of oscillation is it is related to the gate capacitance. So similarly for this case also, if you study the charge stability diagram, then we'll be able to calculate some of the some of the values of this circuit element that we are using, like capacitor or resistor or interdot capacitance. So that is why we study this charge stability diagram to calculate what are the values associated with the charge transport. So if we look at this horizontal line, so this means there is a change in the gate voltage 1, and this change, it is related to the capacitance of CG1. Similarly, in the vertical direction, there is a change in VG2. So this VG2 is related to CG2. And also there is important things to remember is that what is the difference between this, what is the voltage difference between this triple point. One is electron triple point, one is hole triple point. So if you look at this figure, the delta G for the first quantum dot, this is related to both interdot capacitance as well as what is the total capacitance of the quantum dot 2. So just always remember what is the relation and what is the dependence. Okay, because these are a quite long equation. It's quite difficult to remember, but you need to remember what is the relation so that you can solve the assignment problem, also the any questions related to it. And also for the second case where delta Vg2, this also depends on the interdot capacitance as well as what is the capacitance of the first quantum dot. Okay, so only the relation is, if you just remember the relation, then it's fine to solve the problem. Okay, so for now we'll see what will happen in the higher bias region. So we are just studying what is happening in the lower bias region. Now we'll still see what will happen in the higher bias region. Higher bias means we are applying more source to drain voltage as compared to the case where we see in the hexagonal pattern or the square or tittle pattern. So in brief, what will happen is that if we have started with hexagonal lattice of points where the current is non-zero for the low bias case. So when we apply a high bias, this will become a bias triangle in the higher bias case. So this is in brief how the charge stability diagram will change. Now let us see some of the numerical as well as the mathematical details. This it has been covered, so no need to go into the details. Only thing I wanted to focus is that for this slide, remember that these are the points. So I'm telling this again and again so that it will be easier for you to remember. So these are the points, this yellow or the bright yellow or you can say yellow or orange points. They are the reason where the current is non-zero. Okay, so transport happen only at these points. And inside this hexagonal region where you can see the charge is remaining constant, it is only 1, 3 for this one, 1, 2 for this one, and 2, 2 for this one, and like this. So inside this hexagonal region, this shaded region, there won't be any charge transport because the charges remain constant. So I think this is all. This is the two things that you need to remember. And these are some of the experimental validation of what we have seen. That is, we are seeing that we have two triple points. So we can see for this paper, they have experimentally validated the theoretical concept. Okay, so now let us see the transport for higher bias. So for the higher bias reason, so we are focusing on so for the transport to happen, from the source side to drain side or from the drain side to source, depending on the bias, whether it is a forward bias or a reverse bias. So let's consider the case where μs is less than mu d. The chemical potential of source is less than mu d. So that means, what does this mean? The chemical potential of drain is higher than the chemical potential of the source. So this means we are applying positive bias on the source side as compared to the drain side. So when we apply the positive bias, that means it will lower down the energy levels of this the source side or the drain side. Depending on that, the chemical potential will also get lowered. So for this case, the charge transport will occur from, so we have three reasons, right? Sorry, four reasons. Source, then quantum dot 1, quantum dot 2, and drain. And we're starting with, I'm just representing in a simple picture Okay, so I'm not considering any tunnel resistance between this quantum dot 1 and quantum dot 2 or any source to quantum dot 1. So, but they are there, but just to understand the process, I'm just representing without this complete picture. So we are starting with mu d1 is greater than, let's say this is the level for mu d1. This is for the source side. So for this charge to transport from drain to source, so to happen in a sequential manner, so that means the energy level they should be aligned properly. So that means the energy level for, let's say this is quantum dot 2, this is quantum dot 1. Energy level for quantum dot 2, the electrochemical potential, it should be equal to or it can be lower than the drain part, so that charge can transfer easily from the drain to the quantum dot 2. Similarly, for the quantum dot 1, the chemical potential, it should be lower or it can be equal to quantum dot 2. So that the charge will now tunnel to this quantum dot 1, and similarly, the chemical potential of quantum dot 1, it should be equal to or lower than source side, so that the electron can tunnel to it. So the condition that we have is that for charge transport to happen in lower bias case, they need to satisfy mu d1, it should be greater than equal to mu 2. Mu 2 should be greater than equal to mu 1, and mu 1, it should be greater than equal to mu s. Okay, so this is for the transport condition for the higher bias case. In the lower bias case, there is no such condition, because if you recall, uh, all these charge points, all these points where we can see the charge fluctuation, they occur at the same value of gate voltage, or the same value of gate voltage 1 or gate voltage 2. So that means even if we apply low bias, then it's possible to see the charge transport if we apply that gate voltage which will occupy the charge triple point. So if you are studying around the charge triple point, then no matter what the chemical potential, then it's possible to see the charge transport. But for this case, because we are applying large bias, so there is a significant difference between them. So that means we have a condition that they should follow, or they should be energy levels should be aligned properly. Okay. And the limiting case is that if you find out what is the limiting case for this, so limiting case is the case where mu d is equal to mu 2, mu 1 is equal to mu 2, and mu 1 is equal to mu s. So now let us see what is the reason in the charge stability diagram which satisfy this limiting condition. And if we find out find out the area which is covered by this limiting reason, so limiting condition, that means we will be able to see the reason where we can see the charge transfer. Okay, so this, if you look at the graph, should I draw it? I think it's better if no. Let me draw it here. So I'm just drawing the same honeycomb lattice for the high bias case. Okay. So we have a charge triple point. Then there is a blue line here. And there is I think, there is a orange line here. And there is a green line, which is here. So this this blue lines means the mu1 is varying. but mu2 is not changing. So that means for this case, mu2 is aligned with mu d. So it is already aligned. So that means it is not varying for this line. And if you look at the orange line, for this case, I think there is a red line, so orange, right? Yes, there is a red line here. Now we have a blue line and the green line. So for the red one, the mu1, it is not varying. Mu1, it is not varying, but mu2 is changing. So that means for this case, mu1, it is aligned with mu_s. And for the green one, or I think in the graph, it is a blue line, but let's say it is a green line. So for this line, both mu1 and mu2 are varying. So that means mu1 is now aligned with mu2. So we are changing mu1 and mu2 so that they are aligned. Okay. So this is the lines where we see the limiting condition for charge transport. So now let us find out what is the area that should be that should give the non-zero value of the current. Whether the area under this graph is showing the charge transport or area left to this or right. Sorry, left to this or right to this. So we'll see which of this area will show the charge transport. So to see the charge transport, let us say for the case, let's say mu2, it is equal to mu d. Let's say this, we are studying this blue line. So if we consider the region below this line, so we are considering this region below this blue curve. That means in the graph, in the charge stability diagram, this will represent we are decreasing the value of. So we are studying below this blue line. So that means we are decreasing VG2. So we are decreasing the VG2. That means we are increasing the potential of quantum dot 2 in negative direction. So for quantum dot 2, it is increasing in the negative direction. What I mean pictorially is that, so decreasing VG2 means we are increasing the energy of the quantum dot 2 as compared to quantum dot 1. So pictorially, if I present it, so we have quantum dot 2 and we have a drain side. So now we are focusing in an area where the VG2 is decreasing, that is below this blue line. So VG2 decreasing means we are increasing the potential of quantum dot 2 in the negative direction. So that means it will increase this level as compared to the drain side. So you can see it here. No electron tunneling, no charge tunneling can happen if you have a condition like this. So that means the charge transport cannot occur in this region below this blue line. Okay. Now for the second limiting case where we are seeing the area which is right to mu1 equal to mu_s. This area. So for this case, if you look at this charge stability diagram, this means we are increasing the value of Bg1. So the right region is the case where we are increasing Bg1. 1. So that means, so Bg1, it is increasing. So that means the potential of quantum dot 1, it is more positive as compared to the source side. So that means potential is more positive. That means the energy of the quantum dot 1, it will now decrease because we are applying more positive gate voltage. So this will decrease. So if you look at the picture, so this is source, this is quantum dot 1. So now we are lowering the energy of quantum dot 1 as compared to quantum dot. Here we can see that mu1, and this is mu1, this is mu_s. Mu1 is less than mu_s. So that means which we don't want, because for the charge transport to happen, mu_s should be greater than mu1. If we look at this, sorry, for charge transport to happen, mu1 should be greater than mu_s. So that means the reason right to this red line, it won't show any charge transport. And similarly, you can see for the case where we are seeing the reason left to mu1 equal to mu2. So this is the reason. Here also we can see that the transport is blocked by applying the same logic. So by just combining all these lines in this graph, where so we have a line mu1 equal to mu2. This is the line for red one. This is the blue. So this they intersect and they form a triangular region. Inside this triangle, the charge transport can happen, but outside this triangle, there won't be any charge transport. And if you now reverse bias this case, what will happen? We'll see a reverse triangle. Initially, we have a triangles which are oriented in the lower direction. Now we'll have a upward facing triangles where the shaded inside this shaded region, for this reverse bias, there won't be any current. Okay. So this is for the charge transport or the charge stability diagram, where we consider that the charge transport will happen when the chemical potential they are aligned properly, and this satisfies the condition that we have seen earlier. So now we'll see some of the mathematical details of this. Okay. So if you, as I said before, a single quantum dot, we can consider it as a artificial atom, but for a double quantum dot, this we can treat as a artificial molecule. So if we now change the gate voltage, then we can change the energy levels, and we can also change the energy spacing of this quantum dot. So to study this picture or the charge transport quantitatively, so we need to look at what is the energy change after coupling from single quantum dot to a double quantum dot. So for this, we can take help of quantum mechanics. Okay, so I will just give a brief introduction to quantum mechanics, which is required for to understand this mathematical details. So in quantum mechanics, what we do, we represent the particles, or it can be a charged particle, or it can be any particle which we are focusing on. So the particle, it is represented by a wave function psi. So the most important properties, most important parameter in quantum mechanics is the wave function psi, because we can find out many details about this particle by just looking at what is the wave function of this charged particle. So, in quantum mechanics, we just represent the particle by a wave function psi, and to extract the physical parameters, it can be a angular momentum, or it can be what is the linear momentum, or what is the energy of this particle. So um, we operate, we just introduce some operators to this wave function. So for energy, we have Hamiltonian operator. So when this Hamiltonian operator, when it acts on this wave function, then it will give the what is the energy state of this particle. So by operating this operator, which is the Hamiltonian operator for this case, it's possible to extract what is the energy of this quantum dot or any charge particle. Okay, so let us see for how the change is happening from single quantum dot to a double quantum dot. Okay, so for this, let's compare it. So we have a uncoupled state where the quantum dots they are widely separated from each other. So this is well separated quantum dots. Now in the second case, we have a coupled state. This is where we bring this particle, the quantum dot, to a certain distance so that they can couple with each other. Okay. So for the well separated quantum dots, let's say we are focusing on two level system. So we have two quantum dot, which are earlier they are widely separated from each other. So let's say the energy of quantum dot one, it is E1, and the wave function is phi 1. And the energy of quantum dot 2 is E2, and the wave function is phi 2. So these lines, they are the energy level, or we say these are unperturbed energy level. Unperturbed means they are not disturbed even in the presence of a particle 1 or in presence of particle 2, because they are widely separated, so the energy states are remain unchanged. So we say these are unperturbed state. So as I said, when we act Hamiltonian operator on the state phi 1 on the wave function, then it will extract the energy of this particle, and it will keep the wave function unchanged. And this wave function, this is for this type of equation, this is what we call eigenvalue equation. And phi E1 is the eigenvalue, and phi 1 is the eigenstate. So that means when we operate the Hamiltonian operator on phi 1, it is giving what is the energy of this quantum dot 1, and it is keeping the wave function state or the eigenstate unchanged. Similarly, let's say this H is H0, which is the unperturbed Hamiltonian. Now for the second case, we can write down the same equation. That is H0 when it acts on phi 2, it will give E2 times phi 2. And the energy difference between this state is, in the unperturbed situation, we have E1 minus E2 or E2 minus E1, depending on where the energy level E1 can be greater or E2 can be greater. So for now, we are just considering E2 is greater than E1. So we have a similar case where E1 is greater than E2. It doesn't matter. Now, for the second case, where we are bringing these quantum dots close to each other so that they can couple and the energy state can get changed. So because of the coupling, now the Hamiltonian operator for this coupled state, we can write it as H is the unpart of Hamiltonian plus some matrix which is related to the coupling between this quantum dot. So we now have a new Hamiltonian which is H0 times H0 plus T. Okay, so for this state, what will happen now because of the coupling, the energy state will now get changed. Now we'll have a bonding state and we'll have a anti-bonding state. For bonding state, the wave function, it is psi b, and for the anti-bonding state, the wave function is psi a. So that means if you now apply this new Hamiltonian on psi 1, sorry, psi a, this will give E psi a, and when this applies to psi b, it will give EB psi b. Okay, and the energy splitting between these levels, now it is not change, it is EA minus EB. And we have also seen some of the mathematical details. If you look at, okay, yes, this. So EA, it is related to EM. So EM is nothing but the average value of E1 plus E2 by 2. Delta E, it is E1 minus E2. And T12, it is the coupling matrix element. Because of the coupling between two quantum dot, we have T12. So it is related to T, which I've seen in the Hamilton. Okay, so we can represent EA as this form. So it depends on both delta E as well as what is the coupling matrix, tunneling matrix element. And for the bonding state, we also have same type, but now it is bonding state have lower value than anti-bonding state. So we have a minus here, but the expression is more and less same, only different than this minus sign. So EA and EB now will get changed, and from that we can also express the eigenstate psi b as this form. Remember that phi 1 and phi 2, these are the unperturbed state which we have earlier in the uncoupled state. So now this psi b depends both on psi 1 and psi 2 because of the coupling between these two quantum dot. And for the bonding state, sorry, for the anti-bonding state, we can also express this wave form as this equation. Okay, from this, we now have a new, what is a renormalized energy difference, which is the new energy difference in the presence of coupling, and it is the difference of EA with respect to EB. So this is given by square root of delta E square plus 2 T12 square. So we can see here the delta E, the splitting in the presence of coupling. It depends both on what was the what was this energy splitting there in the uncoupled state. Also depends on the tunneling matrix element. Okay, so let us see some of the interesting details of this relation. So this is what has been plot in this graph. So if you look at this graph, So here it's the variation of delta E or the variation of delta E star. It is plotted as a function of energy. What is the splitting behaving like in the function of energy? And for both EA and EV, so you can see they depend on they are like this relation. So these are plotted as hyperbolic function. Okay. And these are dotted lines are for the case where these are the lines for the energy state of E1 or energy state of E2. From this graph, so if you look at the region around which the delta is zero, that is this point. For this point, the delta is zero. You can see the delta is zero. That means the energy level of both quantum dot, they are same. And from the relation of delta E star, which is given by delta E square plus 2 T12 square. So when delta is 0, so that means delta E star, it is given by 2 times of the tunneling matrix element. So this is for this delta is 0, this is the minimum splitting between antibonding and the bonding state that we can have for this double quantum dot system. So this represents the minimum bonding and antibonding energy difference. So when delta is non-zero, then the delta star will now increase in both this direction as well as this direction. But at this point where delta is zero, we have a minimum splitting value of 2 times of tunneling matrix element. Now the second interesting feature is that if you go towards higher value of delta E, that is we are just focusing on higher value of delta E. So if you look at this region, then the EA, the energy of bonding as well as the anti-bonding state, they are approaching what is the energy of E1 and E2. So that means when delta is large, so that means they are quantum dots are far apart from each other. Then the bonding and anti-bonding energy, they will be equal to what is the energy of E1 and E2. Okay, so these are some of the interesting behavior that we can conclude from this graph. Okay, this antibonding and bonding state, this is one type of terminology that we can use. But another terminology is that we can also say these are single state and these are triple state. Okay, so let us see some of the important characteristics of this. So for this two electron double quantum dot, when E1 and E2, when they are same, we have seen earlier when delta is 0, then delta is star is 2 times of, I think the color is not visible. Okay, so when delta is 0, which is E1 and E2, they are at the same level, which is E1 is equal to E2. So that means the splitting between this antibonding or bonding, or we can say singlet and triplet state, we can say that we can write it as 2 times of the tunneling matrix element. So this is what that has been seen in this plot, this energy diagram. So the energy will be 2 times of T. Now if we consider the coupling case, let's say the T is approximately 0. So for this state, the two quantum dots, they are far apart. So they will behave independently. Their energy state will not be changed. So for this state, we can write U. This is the energy state of quantum dot 1. This is the energy state of quantum dot 2. And they are independent. For the large coupling case, where T12 is very large, it is not equal to 0. Now we'll say that we'll see a bonding and antibonding or singlet triplet state, which is formed by the tunnel coupling. So this is represent here. This is EA and this is EB or singlet triplet state. So for the singlet state, which has lower energy as compared to the triplet state, we can make a assumption that it behaves like a bonding state, and triplet state it is like a antibonding state. So if you look at the charge distribution for singlet state, the charge distribution for one of the quantum dot, it is more than the charge distribution for another dot. So charge distribution is asymmetric for the singlet state, and for the triplet state, the charge distribution is nearly symmetric. And from this, we have seen what we can conclude is that for the zero deturning, that is T12 when it is less, then the splitting between this quantum dot is between the singlet and triplet uh, quantum dot system, they are very less. So splitting is very small. But once we have T12 very less, the splitting is very less. And another difference that we have seen also that for a two electron single quantum dot. So if we compare the splitting of singlet and triplet state for a two electron single quantum dot and two electron double quantum dot. So for this two electron single quantum dot, the splitting is very large as compared to the two electron double quantum dot. Okay, so this is what has been discussed in the lecture. So in the next case, what we have seen, so we are now know we have an idea about what is the reason where we'll see the charge transport under low bias, under high bias. For low bias, we'll see the charge transport in the charge triple point. It can be an electron triple point or a hole triple point, or for the low bias case. And for the last bias case, we'll see that the charge transport is it happens when the in a bias triangle, in the area enclosed by this bias triangle, which satisfies the required chemical potential uh, condition. Okay, so now let us see mm, what will be the charge transport in forward bias case and the reverse bias case, in the low bias and the last bias case. For the low bias, what we have seen is that if you consider a case is where the Fermi levels of the first side, or let's say the drain side, it is aligned with the singlet and triplet state of the first quantum dot, but it is not aligned with the singlet and triplet state of the second quantum dot, because here this is here you can say this is 1 1 state and this is 2 0 2 0 state. So the left side is more like a single sorry two electron single quantum dot. So that is why the splitting is very large. But for this one, which have 1 1 state, so it behaving like a double quantum dot. Okay. So that is why the splitting between this singlet and triplet state is less. Okay. And we are considering a situation where we are taking that there is already a spin of electron which is there in the left side. Okay. Now we are adding electron to this system. So that means if we add electron, then And we are seeing that. So depend if you look at this energy level diagram, so you can see that only these energy levels are aligned properly with the Fermi energy. So that means this state won't participate in the charge transport process. So let's say we are coupling, we are adding spin-off state for the low bias case. So this spin-off state, it can go tunnel to this state, but this spin-off state, it can't couple to this left quantum dot because there is already a spin-off state is there. And for the 2 0 state, for for the 2 0 state, if you look at the eigenstate, only the triplet state will allow two spin off or two spin down state to occupy the energy level. In the singlet state, the spin should be flipped. So that is why if you couple a spin up state to this side, then it won't couple to this left quantum dot. But because they have this singlet state have same energy level as same Fermi energy level to the drain side. So this can tunnel back. Now we can add a spin down state. So this spin down now can go tunnel to this side because this right side can accommodate both spin up and spin down. Okay, but for the left side, there is already a spin up state. That means this spin down state now can go to this singlet state and it can go to this. So that means for the low bias case, the spin down state can transport. For this case, it can lead to charge transport. And this is the charge triple point of which we have seen earlier. So this is for the low bias case in the forward bias condition. In the same forward bias condition, let us see what will happen to the last bias case. For the last bias case, what will happen? The Fermi energy of one will be low compared to the Fermi energy of this. Okay. So because of this, what will happen when this singlet state, sorry, when we add this triple, okay, sorry for this state. So when we add the spin up state to this singlet and triple state, so it can tunnel to this first quantum dot, but it can't tunnel to this second quantum dot because of the same reason, because there is already a spin up state is there, and only the singlet state is allowed to transfer participate in the charge transport because triplet state has higher energy. So because of that, this spin-off state can't couple to this second quantum dot. But now the situation is that this spin-off state, once coupled to this first quantum dot, it can't tunnel back to this side. It remains trapped in this region because the energy level for this side is greater than the energy level of the first quantum dot. So that means for this condition, there won't be any charge transport for this spin of state, and the spin is completely it is completely uh, trapped in this inside this first quantum dot region. So if you look at the charge stability diagram, so this will create a black region where the charge transport is not allowed because of this spin blockade. Similar to the Coulomb blockade, we have spin blockade because depending on the spin, the charge transport is blocked. But for this case, the downstate it can couple, similar to the low bias case, only the upstate can couple. So to make this spin up state to contribute to a charge transport or to tunnel to this singlet state of this state, what we can do, we can apply a very, very large bias by changing the gate voltage of. So here you can see that the T levels, the triplet state, they are aligned properly with the Fermi energy level. So once this spin-up state coupled to this first quantum dot, it can tunnel to this second quantum dot, and it can tunnel to the left side. So that means it's possible to see the charge transport in this case, and this will create this rays in this case. For the reverse bias case, we see a different situation. So we see that uh, even in the low bias case, the situation is similar because it's a low bias, the Fermi energy are aligned properly. Both spin up and spin down state can contribute the charge transport, and we'll see the charge triple point here. But for the last bias case, because it's a reverse bias, for this case, the triplet state is already aligned with the Fermi energy level. So that means even if we add a spin up state, it can tunnel to this T20 state, and it can tunnel to this singlet state and triplet state, and you can tunnel to this side. So that means for the reverse bias case, it's possible to see the charge transport even though we have spin off or spin down. So this is what we have seen in this graph. So we see that for the reverse bias case, no blockade region is found, and both spin channel can contribute to the charge transport. So now we'll see some of the uh, questions regarding this concept. Also, let's try to solve the questions that we weren't able to solve in the last live session. Okay, only for a few questions remaining. So we'll solve it first, then we'll try to solve the questions related to leakage. So in question number 9, it says in a stability diagram, which is the plot of differential conductor, where it says the source, drain, bias voltage, and the gate voltage. The Coulomb blockade region often forms diamond-shaped area of suppressed conductance. What does the size of Coulomb diamond in bias direction primarily represent? Whether it represents the maximum possible current that can allow the device at that gate voltage, or it represents the difference between source drain capacitance to the dot, and it says the energy gap between highest and lowest occupied levels, or option D, the range of bias over which no energetically allowed single electron tunneling transistor exit between n and n plus 1 charge states. What does the size of this Coulomb diamond primarily represent? So if you look at the Coulomb, the charge stability diagram, so we have a dot like this. So if we recall, this represent delta Vg, and it is related to E by Cg. So it is related to what is the periodicity of Coulomb blockade oscillation. And for this horizontal direction, this is related to delta Be, which is the charging energy. And this is E square by C. Okay. So that means this Coulomb blockade region, they represent the range of bias over which no energetically allowed single electron tunneling can exit between n and n plus 1 charged. So answer for this is option D. So in question number 10, we have in a quantum dot experiment, you observe diamond shaped zero current region shrinking symmetrically with bias. If the dot material changes from metal to semiconductor, how might the diamond edges logically alter? Option A, diamond expand and as the density of state increase continuously. Option B, they vanish entirely, replaced by linear transport. Option C, edges become irregular due to added discrete orbital levels, complicating pure charge-based boundaries. Option D, none of the above. You can easily guess this option C is the right option because when we go from metal to semiconductor, there is discrete energy level. This discrete energy level become they will make this Coulomb diamond irregular. Okay, so option is answer is option C. Question number 11. What is the role of gate electrode in a single electron transistor? Option A, it fixes spin orientation of electron on the dot through spin-orbit coupling. Option B, it provides additional low resistance path for electron to travel, increasing the total current. Option C, it directly inject hot electron into the dot by bypassing the tunnel barrier. Or option D, it tunes the electrostatic potential of the dot by capacitance, thereby controlling which charge states are energetically favorable. So gate electrode, the role is to tune the electrostatic potential of the dot by a capacitance, which ultimately controls the charge state. It can be n state or n plus 1 state or n plus 2 state. Depending on that, we'll see a Coulomb blockade oscillation at different charge state. So answer for this is option D. Okay, for question number 12, we have for a circular two-dimensional quantum dot at zero magnetic field. What is the degeneracy of second cell? This is a directly mm, conceptual question. So if you recall, the degeneracy of the second cell is 4. Option A. Okay, question number 13. Which experimental signature in Coulomb blockade measurement most directly reflects self-healing in an artificial atom? So, option A, random irregular spacing between conductance peak. Option B, pairs or group of peaks with small spacing followed by a larger spacing. Option C, complete separation of conductance at all gate voltages. Or option D, a strictly linear shift of all peaks with magnetic field without crossing. So the answer for this is option D. So if you recall for self-healing for artificial atom, so electrons will successfully occupy the degenerate states energy levels of same cell like this. Then for the second cell, it has somewhat higher energy. So that means for this one, the energy required is a bit higher. So the Coulomb blockade oscillation will occur at a different value of at a different periodicity. So that means once the orbitals of degenerate states are occupied, uh, next we'll have a second excitation. So for this degenerate energy level, there will be peaks which are spaced in a small interval, and for this splitting, we'll see a larger interval spacing. So that is why option B is the correct option. Okay. Now we'll see some of the conceptual question on week 8. So if you look at question number 1, we have in a double quantum dot system, the tunnel barriers referred to interdot capacitance, which affect the electrostatic potential of both quantum dot, or it's a applied gate voltage across quantum dot 1 and 2, which are capacitively coupled to control the energy level. Or option C, it's a leaky capacitor with a resistor and capacitor connected in parallel to control the electron tunneling across the junction. Option D, none of the above. So in a double quantum dot, what is the tunnel barrier refers to? So answer is option C, because if you see the tunnel barrier, they are nothing but they are leaky capacitor, where we can represent it by a capacitor which is connected parallel to a resistor. So options C. Question number 2. Which of these following is not true for a double quantum dot system under low bias condition? Option A, single electron charging is observed for energy less than charging energy, where electron can tunnel one at a time, which is true. Option B, charge transport is possible inside the area on the charge stability diagram created by the hexagonal lattice point, which is not true, because charge transport is only happening at the triple point, electron triple point or whole triple point. So charge transport cannot happen inside this area. Only for the last bias case, the charge transport can happen inside the area covered by this bias triangles. Okay, but for the low bias case, they occur at the charge triple point. Okay, option B is one of the answer. Let us see option C and D. Option C is spin blockade region are observed under forward bias condition, where Fermi energy of drain align with the S11 and T11 state. So if you recall, for the low bias case, there is no spin blockade region, because both spin up and spin down case, they can tunnel, they can contribute to the charge for the forward bias condition. So that means option C is also an answer. Option D, charge stability diagram changes from square to tilted lattice under the assumption of non-zero cross gate capacitance, which is true. So the answer to this question is option B and D, which are not true for the double quantum dot system under low bias condition. Okay. Question number 3, find out the correct option from the following statement regarding the double quantum dot system under both CM, CG1, CG2 are non-zero. So which of this is true for? Option A, charge stability diagram shows non-degenerate electron and hole triple points where charge transport is non-zero. This is true. These are non-degenerate. If you recall, if you start from N1, N2, or if you start from N1 plus 1 and N2 plus 1, they are two different processes. So it's like if you start from 1, 1, then it will require different value of the gate voltage, and if you start from 2, 2, it will require a bit higher gate voltage. So that means option A is correct, because it's saying it's non-degenerate, so they have different value of gate voltage. Option B, whole triple point appear at a relatively higher gate voltage as compared to the electron triple point, which is also true. This we have also seen the lecture, or this I have also discussed in the first part of this live session. So this whole triple point, which we say 2, 2 point, this appear at relatively higher gate voltage. Option B is also correct. Option C, electron and hole triple point appear at the same gate voltage on the charge stability diagram, which is not true, because for the when all the capacitance are non-zero, this is not true. This is only true when one of the capacitance is 0. Okay. Option D, information about the interdot capacitance or the cross gate capacitance can easily obtain from the charge stability diagram. So CM and CG1, CG2, we can see that these are related to delta VG1 and delta VG2, which is already there in the charge stability diagram, which can be calculated from the charge stability diagram. So that means option D is also a correct option for the double quantum dot for the case where all of the capacitance are non-zero. So answer is A, B, and D. Okay, question number 4. The motion of electron at the hole and electron triple point are same in a double quantum dot system. Whether this statement is true or false. So this is a true statement because electron transport is same if you either look at the electron triple point or the hole triple point. So they are the same. True. Option, sorry, question number 5. Find out the correct statement regarding the anti-bonding and bonding state of a double quantum. So it's written well, but it's a dot. Double quantum dot system. Option A, energy splitting is independent of energy levels of isolated dots and tunnel coupling. This is not true because if you recall, the energy splitting between the antibonding and bonding state, which is A minus EB, this is given by square root of delta E square plus 2 times T12 square. So this energy splitting, it depends on the energy level of isolated atom, which is delta E here. And it also depends on the tunnel matrix element, which is T1. So that means option A is not a correct option. Okay, let us see option B. Option B is energy splitting remain unchanged under zero tunnel coupling. Okay, so we have T1 to 0. So this means delta E star is delta E because in this equation T12 is 0. So this means this is E1 minus E2. So whatever energy splitting we have earlier, now we have the same energy splitting in case of zero tunnel coupling. So option B is one of the correct option. Option C, energy of the antibonding state is higher than the bonding state, which is also true because if you look at so if you start from a situation where E1 and E2 are equal, just to see what is the position of bonding and antibonding state. So if E1 is equal to E2, so if you look at the mathematical relation, EB, so this is EB, this is EE. So EB, it is given by EM minus square root delta E square by 2, I think, or so it depends. Let me see where. So if we look at the relation, yes, this one. So EA, it is EM plus this value and EB is EM minus the same value. So that means the energy levels of antibonding and bonding state, they are different, and antibonding, it is at higher energy level as compared to the bonding state. So option C is also correct. So the correct options are B and C. Option D is not the answer because it says none of the above. In question number 6, in a charge stability diagram in the low bias case, what defines a triple point for a double quantum dot system? Option A, it's a region where transport is completely blocked for all the gate voltages. Option B, it's a point where three different charge configurations are simultaneously occur at the same gate voltage, which seems a correct option. So B is correct. Let's see C. It's a point where charge transport is allowed even under low bias condition, which is also correct. Option D, any intersection of charge addition line regardless of the degeneracy, which is not correct. So the charge stability diagram, the triple points are a point where we see degeneracy of three charge state, and also it's a point where the charge transport is allowed even under the low bias condition. Okay, just go through the question number 7 once. So for question number 7, it says, how does a significant cross gate capacitance, each gate strongly affecting both gates, modify the orientation of charge transition lines in the BG1, BG2 charge stability diagram? Option A, cross gate. Okay, so there is a spelling mistake. So it's a gate capacitance. Cross gate capacitance has no effect on line orientation, only on spacing, which is not correct. Option B, lines for um, dot 1 remain perfectly vertical. Lines for dot 2 remains perfectly horizontal, which is also not true. Option C, it causes charge transition line to curve into a parabolic ones, which is also not true. Option D, all charge transition line acquire mixed slope, more non-purely aligned with the single axis, which is true. Because for the cross gate capacitance to be non-zero, we have seen tilted uh, pattern, where both the VG1 and VG2, the pattern get tilted because they are affecting one another. Okay, so that is why answer for this is option D. So we'll solve question number 8, then we'll end the session. For question number 8, it says in the transport measurement, what is the characteristic signature of Pauli spin blockade in a bias triangle of a double dot stability diagram? What is the characteristic signature of Pauli spin blockade in a bias triangle in a double dot stability diagram? Option A, it's an increase in current at all points inside the bias triangle. So inside this bias triangle at all points, we see a increase in current. Option B, a periodic oscillation of current as a function of magnetic field inside the triangle, which can indicate the polyspin blockade, which is not true. Option A, it says a complete disappearance of the bias triangle regardless of the gate voltage, which is also not true. Option D, a region within the bias triangle where current is strongly suppressed for one bias polarity, which is true because if you recall, If I just show the plots, this one. So for the biased triangle, you can see we see a black region where one of the spin is not allowed to tunnel to the other side of this circuit because it's not energetically favorable. So that means answer is option D. Okay. So these are some of the questions related to the concept of wicket, which basically covers the double quantum dot system and what is the charge stability diagram. And we'll solve few more problems related to the concept of this week, also related to concept of week 9 in our next lab session. So I hope the problems that I've solved, it will be helpful for you. Please go through in the details. Also, try to try to see the lectures or the first part of the live session again to understand the concept better, and so that you can solve the assignment problems. Okay. So most of the problems are more and less conceptual. So it's crucial to it's for you to go through the concept in detail so that you can solve the assignment problem. Okay. So for today, we'll end our live session. So thank you for joining the session. I hope we'll meet on next Friday, same time from 6 to 8 to solve few more problems related to week 9. Also to see what is there in week 9 apart from week 8. So for now, goodbye everyone.